12 chemists, welcome to TP's Chemistry Cuts. In this clip we'll work through 3 examples of calculating an empirical formula using percentage composition data.
So what we're going to do is work through 3 different examples of empirical formula from percentage composition. So 2 things to be aware of there. The first thing is, what do we mean by percentage composition? Percentage composition is just, if you have a substance, you can work out for each of the elements what percentage of the total mass is due to that individual element. So when you consider all the elements, they add up to 100%. And you can gain those measurements from, or you get those from experimental measurements. Next year you'll look at a topic called spectroscopy, which is one of the ways of doing it. There are other ways. So that's available to us, and it's a relatively straightforward thing that just takes hours to do for each compound. So it's pretty straightforward, and you get these given to you. What you then can use them for is to work out an empirical formula. And to remind you, an empirical formula is the simplest of the formulas. It gives you the simplest ratio of elements in a substance. Okay? So if we looked at calcium chloride, as the example I've given there, at the simplest level, it means if you take a particle of calcium chloride, it's got 1 calcium and 2 chlorines there. But we want to do this in a more meaningful way, and so we can scale it up. So instead of 1 of each, we talk about 1 mole of each. So this means then for every mole of calcium, we have 2 moles of chlorine. Okay? So how do we go from a percentage composition to the empirical formula? It's relatively straightforward. What we have, and you don't actually need this, is n equals little m over big M. Okay? And that's a way of converting between masses, the little m, and amounts. So what we need to start all of these measurements, or all of these calculations with, is getting, instead of a percentage, a mass. And we saw last lesson there's a very, very simple way of doing that, and that is what? No, we've got percentages there. How do we actually...
You assume that there's 100 grams?
Yes, exactly. So if we assume for each of these that we have 100 grams of substance, that means that each of the percentages just transfers into being a mass. Okay? And so that's the first step. Assume 100 g of substance. Okay? So which one do you want to do first? Should we do this one? Yep. Okay. So, in that case, we have 53.6 g of carbon, 8.9 g of hydrogen, and we've got 37.5 g of nitrogen. So we've got our mass. We can now convert to an amount, because that's what we need, because the formula is telling us the ratio of amounts in a substance. And so we need to divide each of these by an atomic mass. And if you look in your side pads, usually it's the back page, you'll find you've got a periodic table. We will give you a periodic table on the day when you're doing the calculations, so use the numbers there. Okay. So if we look at carbon, okay, we can convert this to an amount. Convert to amount in mole using n equals little m over big M. So here it's 53.6 and carbon is 12.0. Somebody can work that out. Hydrogen's nice and straightforward, it's 1. And then we've got 37.5 divided by 14 for nitrogen. So we use nice round numbers. So if somebody could tell me what this one is?
4.46. Oh, 4.47, sorry.
4.47 mole. Okay. We've got 8.9. What about this one?
2.59.
2.59. Now, that's telling us then that the formula is C 4.47, H 8.9 and N 2.59. Well, that's not the simplest ratio, so we can't use that as our formula. So how can we simplify that as our first step?
Divide by the smallest?
Yeah, so if we divide by the smallest number, it means that one of the elements at least is going to be 1 to something, yeah? So the smallest number is 2.68, so divide by smallest number. So if we divide 4.47 divided by 2.68, what does that give me?
Uh, 1.67.
1.67. Oh dear. We have a problem, Houston. Okay, carry on. 8.9 divided by 2.68 is equal to
3.32.
3.32. Oh dear. And then we've got 2.68 divided by 2.68. I think I can do that one. 1. So it's telling me I've got 1 nitrogen to 3.32 hydrogens to 1.67 carbons. Is there any way I could simplify that? Think about what an empirical formula is. It's telling you the simplest ratio. What we're assuming is that that simplest ratio is going to be 1 to something to something. And it obviously isn't 1 to something, is it?
Would you like times by 100?
Not times it by 100. Times it by a small number that might actually turn all of those into nice round numbers. Think about what this is. What's that a rounded version of? A fraction. 2/3. 2/3. What's this a rounded version of, or almost? A third. So what might be a good number to multiply by 3 to get rid of those awful 3? So if you see anything that's got a 0.66 or 0.67 or a 3.32, it's telling you it's not a 1 to something, it's a 3 to something. Okay, you'll see what I mean when we've actually got the formula. So multiply by 3, and so if I multiply 1.67 times 3, what do I get? 0.67 times 3 equals 5. Okay, 3.32 times 3 equals 10, and then 3 times 1 equals 3. Okay, and that's telling me then that the formula is C5H10N3. Okay, and if we look carefully at that formula, it sort of starts to make sense, because what we started by doing was dividing by the smallest number that would give us 1 to something. In fact, it's 3 to 10 to 5. So we needed to multiply everything by 3 to get it like that. Yeah? Should we try this one? Any problems with that? Yes, Miss.
So do you just round it up to like 5.01?
Yes. Now, you've got to show some common sense here. If you get something like 5.95 and you want to make that a nice round number, you're going to multiply it by a pretty big number to get it up to a full number, so that everything else is. So if you end up with a formula like C60, H48 and 20, you've probably overdone it. Yeah, so use a little bit. Nothing will be much more complicated than this. Maybe it will go up to C10 or something, but you won't get C60s and C40s and 30s. Yeah? Right, so let's do the next one. Okay, or do you want to do, which one do you want to do? The next one. Okay, let's keep on keeping on. Okay, 52.2 grams, 13.0 grams, and 34.8 grams. So that's just assuming 100 grams. Okay, we've got masses now. We don't want masses. You can't use masses directly for a formula. You need to convert them to amounts, because that's what an empirical formula is telling you the ratio of. So we divide by the atomic mass for each one. So we've got 52.2 divided by 12 for carbon, 13.0 divided by 1 for hydrogen, which I can do, and 34.8 divided by 16.0 for oxygen. Anyone?
4.35.
4.35, 13, this one, 34.8 divided by 16, 2.1? 1.18, yep. Okay, so divide by the smallest number, we've got 4.35 divided by 2.18, somebody could do that, 13 divided by 2.18, and I'll do the last one in my head because I'm brilliant like that.
Just two.
2.
5.96.
So if you get that, what would you do? 6. Okay. So the answer is C2H6O, which is ethanol. Let's do the last one. 37.5. It's good to see that quite a few people are already most of the way through it. That's good. 12.5 G, 50 G. So we need 37.5 divided by 12. 12.5 divided by 1. And 50 divided by 16.0. So 37.5 divided by... Anyone?
3.13. 3.13.
So what am I going to divide by? Yeah. Yep, so divide by 3.13. Somebody could do the middle one for me, and I'll do the outer two. 12.5 divided by 3.13. What's this one? 4. So you've got CH4. Okay. Now, the only other thing to point out is, in this case, we've multiplied by 3. There might be a case where you see things that are 0.5s in them. What would you do then? Multiply by 2. So if you end up with, it means that it's something like C2 something something, and you can't make it any simpler than that. And if you get 0.25s, then you'd multiply by 4. Okay. Anything other than that, you've made a mistake, because we wouldn't push it any further than that. I think we'd be pushing it multiplying by 4. But if you see anything with 0.5s by 2, 0.25s or 75s, then you're going to have to multiply by 4. Okay, any questions about that?